So we have now seen all the rules of symmetry and how to apply those rules to actually get to the stage of symmetry operations followed by character table and all. So given a molecule, we can identify what are the symmetry elements present, what are the symmetry operations present in the molecule, what is the point group of the molecule, and then using the rules of great orthogonality theorem or using unit vector transformations, etc., we can identify what are the IR representations. And we have also seen, if we write a reducible representation, how to convert that into a irreducible representations. So all those rules form the first part of this course, and now the second part is the applications part. So let us start seeing applications of group theory now, okay, in chemistry. Okay, so a few applications we have already discussed. For example, the first one was dipole moment. Whether a molecule has dipole moment or not, we can predict based on the rules of symmetry, right? And then similarly, we have also seen whether a molecule is optically active or not. Optical activity we tested, again using the rules of symmetry and group theory, right? So these two applications we have already seen. So now let us look at group theory and quantum mechanics. Okay, so why are we discussing quantum mechanics? Okay, we'll first we'll just revise. You all must be aware of this famous equation, h psi equal to E psi, right? So what is h psi equal to E psi? It's a eigenvalue equation. And it's also called as Schrodinger wave equation, right? So what are different parts or different components here? So psi is a state function, also called as wave function or wave function, which tells you about the state, all the properties of that particular state. Then H is Hamiltonian operator. That also we know, we might have studied at some point. Hamiltonian operator operates on a function, and if it is a eigenfunction, then it generates eigenvalue, which is energy of the system, right? So basically it's an operator to measure energy. So these are the main components. So we have an operator, we have a function, and then operator operates on a function to give a constant value, which is energy in this case, because the operator is Hamiltonian. So now, why are we discussing Hamiltonian in group theory? So if we see that there is a very important property, which is if we replace, or if we, okay, let's stick to the word replace. So if we replace identical particles in a molecule with the same particles or with identical particles, for example, if we have electron and one electron is replaced with the same electron, then the energy of the system is invariant. So what do I mean by that? So let's say if we have a molecule, let us take an example of methane, and let's call this configuration as configuration 1. If I'm doing any symmetry operation R, it goes to equivalent configuration, right? And let's call this equivalent configuration as 2. Now if you look at, let's say that the symmetry operation is C3, okay? So then we'll be rotating this molecule about the CH bond by 120-degree angle. So now if you see that this atom is replaced with this with this, and so on, right? So basically particle which is the atomic nuclei here, each of this is replaced with the identical ones, and thus the energy of the system, if we measure energy of system 1, configuration 1, should be equal to energy of the system 2. Similarly, we can say about the bonds also. So if this bond, the electron density here is replaced with this electron density versus electron density here is replaced with that electron density. So these are all identical particles because they have similar location with respect to any particular point in the molecule. So that means that we are moving these identical particles around, and in the process we are not perturbing the energy of the system, right? So if I want to write this statement, what do I say? That any two So Hamiltonian does not change or energy does not change. So that means whether I'm measuring energy first or doing a symmetry operation first, it does not matter. So in other words, what we can do is we can say that if we first measure energy on this and then carry out symmetry operation, that should be equal to if we first carry out symmetry operation on this and then measure energy, right? So there is no difference if we first measure energy versus if we first do the symmetry operation. The energy of the system remains invariant. So that tells you that HR is basically equal to RH, which means that H and R commute with each other, right? So we know what is the meaning of commutation now. So H and R, so basically Hamiltonian commutes with all the symmetry operations present in the given molecule. Okay, so we can also say that the Hamiltonian commutes with, in a similar way, we can say that Hamiltonian commutes with a constant, right? So we can write H C psi is equal to C H psi is equal to C E psi, right? So similarly here we can write H R psi. The only difference is that now R is not a constant, R is an operator in itself, right? And we can say that it is R H psi, and this now gives you energy, so R E psi, and we can actually take E out of this operator because now operator will not act on constant, so we will say that E R psi, right? That is very straightforward to see. So now we can see that since psi is an eigenfunction, R psi is also an eigenfunction, right? So we can say R psi is also an eigenfunction, right? So that is easy to see. Now we also know that psi is normalized. So now if we want R psi also to be normalized, what condition we will have? So we will have R psi should be equal to plus minus 1 psi, right? So that means if we operate a symmetry operation onto a wave function which defines the state of the molecule, and the symmetry operation must belong to the molecule. So then state, that symmetry operation will generate a character which is plus or minus 1 because of the above condition, right? So this means that if we are carrying out, given that a molecule has certain set of symmetry operations, if we carry out all those symmetry operations on psi, we will get tau psi. So let's say that if we have E, A, B, C, and so on symmetry operations in a general group G, then we will get plus minus 1. So here we'll always get plus 1 because it's the dimension, but we will get plus minus 1, right? So any symmetry operation if we do, we'll either get plus 1 or minus 1. I mean, of course, if there is mixing of two states involved, then we might get higher state, higher dimensional representation, but mostly we will see that this will be a irreducible representation because we are getting one-dimensional matrix, and one-dimensional matrix we will not be able to reduce it further. So this would then be a irreducible representation, right? So now let us take an example to show what we are saying here. So let's take an example of C3V only. We have been looking at this molecule since we started this course, so we know in and out of all the character table and symmetry operations and everything, so it will be easier to see. Okay, so now if we look at the central atom, which is nitrogen, it has 2px and 2py orbitals, right? So we can take these as the basis set. This is our basis set. So like we took psi as the basis set here and developed a irreducible representation. So this is also a wave function. We can write the wave function for px orbital and py orbital, and we can treat that as basis set and see what representation do we get, whether it's reducible, irreducible, and so on. Okay, so px orbital has the functional form of psi r sine theta cos phi, and py has the functional form of psi r sine theta sine phi. So I'm not going to discuss how we get this px and py. That is discussed elsewhere in quantum mechanics course, so we'll not go into those details. So let us see what is the meaning of this r, theta, and phi. So let us say if we have a point in three-dimensional space, the coordinates are x, y, z, and length of that vector from origin is r. So theta here is the angle with which it is going away from z-axis. Okay, so that angle which this vector is making in three-dimensional coordinate system with z-axis. So how far down basically that vector has fallen from z-axis will be called as theta. Okay, and now if you take a projection of this vector onto xy plane, so this is the projection here, this length, and that projection, if the angle between that projection and the positive side of the x-axis is called as phi. Okay, so this is phi, theta, and r. Now let us see that what happens under different symmetry operations present in C3V onto these theta, phi, and r, because we need to calculate the effect of those symmetry operations onto px. So we should know the effect of symmetry operations onto theta, phi, and r, right? So let's say, so the symmetry operations what we have here is C3V, and let us discuss only one of the class elements, and let's call this as xz, and this will be our term. Okay, so let's say what happens to r. So psi r under E, does it change? So because r is a constant, r is the length of the vector, and as such E does not do anything, so psi r remains as psi r, right? So we don't need to consider any effect of identity onto psi r. Okay, now C3 on psi r. Now this is just the rotation, so rotation is not going to change the length, so again this will be psi r. And similarly, the reflection is also not going to change the length, so this will also be psi r. So basically psi r is invariant under any of these symmetry operations, so that means the character will be +1 in for psi r, right? Okay, so now let's see what happens for to theta. So if we see carefully, theta is the angle which is between the vector and the z-axis. Now all our rotations are with respect to z-axis, right? Because our C3 is lying along z-axis, so all our rotations are about z-axis. So no matter how much you rotate this angle about z-axis, the theta will not change. So that means theta 1 must always be equal to theta 2, where this is angle before symmetry operation and this is angle after symmetry operation is performed. So this means other component sine theta, that will also not change. So that will also remain same, right? Under both C3 as well as sigma xz. Now because sigma xz, why sigma xz will also not change? Because sigma xz contains the z-axis, so the theta with respect to z-axis will not going to be different. Okay, so now let us look at phi. So phi 2, if we are doing a C3 rotation, what happens to phi 2? So phi 2 becomes phi 1 plus 2 pi by 3, right? So we are taking this vector and rotating it by 120 degrees. So that means your new phi will be phi plus 2 pi by 3, phi plus 120 degree. So we can say that phi 2 is equal to phi 1 plus 2 pi by 3. Now this means that what happens to cos phi 2? This will be cos phi 1 plus 2 pi by 3. And we can always write this as cos phi 1 cos 2 pi by 3 minus sin phi 1 sin 2 pi by 3, right? So this is cos a plus b is equal to cos a cos b minus sin a sin b. Okay, so now what happens to cos 2 pi by 3? This is minus half, so you have minus half cos phi 1, and sin 2 pi by 3 is plus root 3 by 2, so you have minus root 3 by 2 sin phi 1. So cos phi 2 is equal to this when I am doing a C3 operation, right? So this is for C3 operation. Now let's see. Okay, we also have to calculate for sin phi, because there was one more term in phi which is sin phi, right? So let's also calculate for sin phi. So under C3, phi 2 equal to phi 1 plus 2 pi by 3. So if we have sin phi 2, this will be equal to sin phi 1 plus 2 pi by 3. Now this is sin a plus b, which will be sin a cos b plus cos a sin b. right? So this again becomes minus half sine phi 1, and this becomes plus root 3 by 2 cos phi 1. Now let's calculate under sigma xz what happens to phi 2. Okay, let's go back to the coordinate system. So if we are having sigma xz, phi will be reflected to minus phi, right? So that means I can say that phi 2 is equal to minus phi 1. Okay, so you can see that, right? My new phi will be somewhere around here, right? So this will be my phi. So this will be a negative angle. So that's why you have phi 2 is equal to negative of phi 1. So now if you want to calculate for cos phi 2, this will be equal to cos of minus phi 1, and if we want to calculate for sine phi 2, this will be equal to sine of minus 5, right? So this will be equal to cos of phi 1, and this will be equal to minus sine phi 1. So now that we have calculated, let us calculate the effect of this different symmetry operations onto all of the elements, which is psi r, sine theta, cos phi, and sine theta, sine phi. So now let us calculate the effect of E onto Px. Now we can do that, right? So E when operated on psi r, sine theta, cos phi, what do I get? So I get the same thing, right? So I get psi r, sine theta, cos phi, and I can say that this is Px. Now let's do the same thing for C3. If I do C3 on Px, I do C3 on psi r, sine theta, cos phi. And what do I get here? So I'll just write down the answer here. So psi r does not change and sine theta does not change, right? So I will say psi r, sine theta, and cos phi changes to cos phi 2. Now that cos phi 2 will be given by minus half of cos phi 1 minus root 3 by 2 of sine phi 1. Right? So I can say that this is minus half cos phi minus root 3 by 2 sine phi. Okay, now I can expand this further and I can say that C3 onto Px will give me psi r sine theta, minus half can come out and this will be cos phi 1 and minus root 3 by 2 psi r sine theta, and we will have sine phi 1. So all I have done is I have just expanded this bracket over here to get this. And now what is this? This is minus half of Px minus root 3 by 2 of Py. So basically upon doing C3 operation onto Px orbital, it gets mixed between Px and Py orbital, right? Okay. Similarly, now we do C3 onto Py, and what do we get? We'll get C3 onto psi r sine theta sine phi, right? So this will now be psi r does not change, sine theta does not change, and sine phi becomes sine phi 2, which is, so I can say this is sine phi 2, and this will be psi r sine theta. This I can write as minus half sine phi 1 plus root 3 by 2 cos phi 1, right? So this again is coming from effect of C3 onto here. Effect of C3 onto sine phi 2, which gives you minus half sine phi 1 plus root 3 by 2 cos phi 1. Okay. Now if you expand this, what do you get? Minus half psi r sine theta sine phi 1 plus root 3 by 2 psi r sine theta cos phi 1. And this in turn can be written as minus half py plus root 3 by 2 px, right? Now similarly, so this is for C3. Ideally we should also do it for C3 square, but we'll just skip it because we just want to see how the matrix is looking for the C3 operation. For sigma xz, what happens if we apply sigma xz onto px? If we do that, we will have sigma xz applied on psi r sine theta and cos phi. So this gives us, so psi r does not change, and so is sine theta, that also does not change, and we have cos phi 2, right? Now cos phi 2, in terms of when we did sigma xz on cos phi 2, it remained same, so I can write it as psi r sine theta cos phi, which is nothing but px, right? So px remained as px. Now let's do sigma xz on py. Now we'll see that this will be sigma xz on psi r sine theta sine phi, and this turns out to be psi r remains as psi r sine theta, and this becomes sine phi 2, right? And we are seeing that it was sine phi 2 is equal to sine of minus phi 1, and we get negative sign out. So psi r sine theta sine phi, which is nothing but negative of py. So sigma xz on py gives you negative of py. So that means if we want to write the matrix for E, what we will get is 1 0 0 1. If you want to write the matrix for C3, this will be minus half minus root 3 by 2 root 3 by 2 minus half, and for sigma xz, this will be 1 0 0 minus 1, right? So basically this comes if we are doing E onto px and py, we have to do it together because they are getting mixed. Then what is the form we are getting here in terms of px and py? And this basically helps you give this matrix, right? Similarly, if we are doing C3 operation here, then px gets transformed into what and py gets transformed into what, and that will give you the matrix for C3, which is this. Similarly for sigma xz. Okay. So now there is very important thing which we want to see, that this actually belongs to, if we look at the trace here, this trace over here for E C3 and sigma xz is nothing but 2 minus 1 and 0, right? So you can say this tau px py for C3. Now we know that this is the trace for E representation under C3V point group. So we can say that the tau px py is nothing but E representation, right? And E representation has basis as, like if we write down it here, E 2 minus 1 0, the unit vector basis for that is x and y, right? So it is transformed as x and y. So px and py orbital, because they are lying along x and y, so they will also transform as x and y, right? So they will also form the basis of E orbitals. Actually, this is the reason why this particular function, which is given by px, is called as px, because to start with, we didn't know whether this function is lying along x-axis or this function is lying along y-axis. But now, as it turns out, it lies along x and y-axis, which is clear from group theory, this character table, right? So this means that we can now name this orbital as px orbital. What I mean is that to start with, we only had these functions. We did not know whether it's px or py, right? When we get the result of quantum mechanics, when we solve the equation, we'll not go into details how we get the px and py orbitals, but when we solve the equations, we get this orbitals, but we don't know whether it's px and py orbitals, which we get to know from here, that this indeed is px and py, because it is transforming as x and y, transforming as E representation under C3 viewpoint group. So we have seen today a very important role of group theory, where wave functions can be taken as basis set and their properties can be discussed whether they are lying along x and y axis or not. We will see more into this when we'll move to symmetry adaptive linear combinations. So that's all for today. And if you have any questions, we'll discuss in interaction session.